start petrified forest time, we're about 4 degrees above the equator. By the time we finish petrified forest time, we're about 10. If you went to the equator today and traveled northwards, what would you see? You get subtropical here.
Rainfall.
Here you get Sahara Desert. As the plate's moving northwards, our climate is going to change. We actually can see this in the rocks. So the thing that I was interested in is, where does that change occur? Once we got the rocks in the right order, we realized that they were actually distinct from each other. And we actually found the horizon where it occurred. It's about a 3 meter, so 12-foot thick horizon right outside here. Below it, we find one fauna and flora. Above it, we find the other fauna and flora. This is what we call our Sonsala member of the Chinle Formation. Now, when we plot our animals, the ones that we're really interested in characterize our lower and upper faunas. Okay, so our interval between our two faunas is this purple band. When we originally found this, we knew that the plants changed somewhere here as well, and believe it or not, it's actually figured out based on pollen. We actually get fossil pollen out of all these sediments, and our pollen assemblages, which are, you know, indicative of your overall plant communities, changed somewhere in here. So we didn't know anything about the pollen through this whole interval. We knew it changed somewhere in here, but we didn't know where. And wouldn't it be really interesting if it changed where the animals did in this purple layer? So we brought in a master student from the University of Utrecht last year in the Netherlands, and he sampled all these beds, and he was actually able to find where the pollen changed, and it does. It changes at the purple layer too. So he gets the older pollen assemblage, starting pretty much where the animals do, up, and then we know the lower pollen assemblages in the sandstone that we're standing on. So this purple horizon is our target. That's where our animals and our plants change.
Right now we're walking in this modern wash, which is actually a good place to find fragments. You won't usually find things in situ, which means that they're in place where they died. You'll usually find them after they've been washed downstream. But you can still use the fossils just to describe them physically. It's still important that you know the fossil came from this level or higher. We know it wouldn't have come from something lower. If it's just a fragment, you can't always be positive that it hasn't been transported at some point or another, but if you find it, oh, she found something right now.
Dinosaur snout bit.
Oh, excellent.
Good. Where the teeth go in it. Well, unfortunately, it's just a little broken bit from in the wash, so I could go back and try and trace up the wash and see if there's any more of it coming out, but I can tell that it's a bit of the snout of a phytosaur, because you can see there's the little holes where the teeth went, and phytosaur would be the only thing with a narrow snout like this.
So something like this, even though that we can tell that it's a phytosaur, we wouldn't actually take it with us because it's not diagnostic of the exact type of phytosaur that it is. The parts that we use to diagnose the type of the phytosaur right now are these knobs on the back of the head that Bill was talking about earlier called squamosals. So if we see an isolated squamosal, we'll pick it up. But something like this, you can't tell just by this piece exactly what it was. So even though it's cool to look at and really fun to find, it's not actually something that we'd keep. But we actually spend a lot of time in the laboratory just studying shapes. It's kind of like puzzle pieces that you start to look and say, hey, that looks different than a rock.
My name's Kenny Bader. I'm the fossil preparator at Petrified Forest National Park. My job is to take fossils that are found out in the field, which they wrap in burlap and plaster. My job is to clean away all the dirt and rock, exposing the fossil. In this case, we have part of the armored plate from the back of a armadillo-like reptile called an aidosaur, and add different types of glues and adhesives to the specimen. We have super glues, we have reversible glues, that are acetone based that I'll add to the specimen. The idea is to fill in all the cracks and prevent the specimen from falling apart. Once it's removed from this plaster jacket, it can be freely handled and won't fall apart. I can use the super glues actually. I can add it to the seams and glue larger pieces together. And in some other cases, certain limestones, we can actually put the fossil with the matrix, the hard rock around it, into a bath of 10% acetic acid, basically vinegar. And we can put it in there and let the acid slowly eat away at the limestone. We have a variety of tools, and this is called an arrow. It's basically a miniature jackhammer. It's also referred to as a micro jack, and it's air-powered. Little needle that vibrates back and forth, and I can use that to slowly chip away the harder rocks off the bone. If it's softer, I can use hand tools like a pen vise or dental picks. Another project that I work on is I go through and mold and cast copies of the fossils, and in most cases at museums, if you look at a display in a museum, if the fossil is not in a glass case or has some other major barrier, then in many cases it's a copy of the fossil. Ideally, I can get the fossils put together just about perfectly, and we'll have an intact bone that can be used by scientists for describing new animal species.
We know this is a tooth, because that's tooth in animal, is the wear surfaces, and this is the root of the tooth, but we have no idea what type of animal this is. Some people have said fish, some people have said reptile. We don't know. So this is the only specimen in the world of this animal. Here's our crayfish. We can't touch him. Part and counterpart. We have a lot of these lower jaws of phytosaurs, but we don't know what species they are. Yeah, it was probably our top land carnivore at the time. So the implications of it is we have an opportunity here to demonstrate a point in Earth's history where the ecosystem at the time was affected, possibly affected by, a major, global disaster, mainly an asteroid impact or a meteorite impact striking the Earth. That's pretty exciting because, for one thing, there's only been one other case where someone's able to pinpoint where that's ever happened, and that's at the end of the Cretaceous with the dinosaurs. The other implication of that, though, is it shows that an event like that isn't necessarily that catastrophic. The blip that we're seeing here is actually pretty minor. We have a couple things go extinct, possibly at that level, but most of it is just a turnover at the species or genus level. But those types of animals still go on, it's just different species. Thing here about the climate change crisis we face today, that's a different story. We can actually see through the rocks the climate change. It goes from very wet, humid, to definitely more arid and drier. In fact, the time we see this drying period culminate is the time when we start to lose a lot of animals. It was a major extinction in Earth's history. Now, whether that was driven by this extreme climate change or from the eruption of magma, all these basaltic rocks that were in place after North America split apart from Africa and South America, we don't know, but it's all part of the picture. But one of the things it shows is that, climate change is real, it happens. What we're still kind of working on is what that can tell us about today. I mean, what it tells us is that it's happened in the past. Things aren't static, things change all the time. And there's a normal cycle to things. And here's a direct evidence of it, 200 million years ago.